So today we're going to talk about solubility, which is an important physical property, okay, of materials. A lot of this is going to be terminology, okay, so learning some vocabulary, and probably a lot of that vocabulary will seem familiar. You've probably covered it at some point, okay. We're also going to learn how to use the solubility chart that is on the back of your periodic table. Okay, so if you flip your periodic table over on the left side, there's a solubility chart there. Okay, that allows us to figure out whether something will be soluble or not. Okay, and we'll go over how that works. And then we're going to talk about why. Why water's weird. Okay, because it seems like in chemistry, if there's a rule, water's the exception to it. Okay, water just does all these things that most other materials do not do. Okay, and so we're going to look at kind of why water behaves that way in terms of how it's structured. Okay, so those are the key points for today. Okay. All right. So obviously, some substances dissolve better than others. Okay. If I'm, like, say, making, Kool-Aid or lemonade, or making one of your athletic drinks, and you have to shake that stuff. You have to shake it to dissolve it. Okay. Some things dissolve real easy, like sugar dissolves pretty easily in water. Salt dissolves pretty easily in water. Right. There's lots of things that do, but there are other things that don't. Like obviously butter. Okay. Like you can't put butter in water and have it dissolve. Okay. You might be able to mix it in, but as soon as you stop stirring, it'll come to the top again. Okay, so there's a difference there in solubility. Some things are soluble, that is, they do dissolve, and some things are insoluble, okay, or less soluble than others. All right. So solubility is that physical property that tells us how much of something can dissolve in something else. Now, what are some things that affect solubility?
Agitation.
Agitation is one.
Temperature?
Temperature is another.
Size of the container.
Well, size of the container, because it allows you to put in more of the solvent, yes. So the amount of solvent would certainly be a part of that.
Surface area.
Yep, surface area for sure.
Agitation.
Yep, we had agitation. Okay, so all of those things can affect how much of something I can dissolve. Okay, like back in the day when we used to make Kool-Aid, I don't know, it's hard to find that anymore. Probably had some horrible thing in it. Okay, but I drank a lot of it as a kid. What I would do is I would actually make my Kool-Aid with warm water, because then I could get more sugar to dissolve in it, and then I would put it in the fridge. Okay, and I knew it was perfect if after a few hours it was nice and cold and there was this little thin layer of sugar on the bottom of the pitcher. Okay, because I knew then that the maximum amount of sugar was dissolved in the Kool-Aid, because no more could stay in solution. It was starting to precipitate out at the bottom. Okay, that means it was going to taste really, really good, because it was saturated essentially with sugar at that point.
Sorry, I missed. There was three, right? Agitation, temperature, what was the other one?
Amount of solutes. Amount of solvent. Amount of solvent. I said solute. Actually, both. All right, so you can get these things to dissolve if you do certain things. You can get more of them to dissolve if you change the conditions a little bit, or less of it to dissolve if you change the conditions. Okay, so what we're going to look at is some of this solubility stuff and kind of how it's going to relate to reactions a bit later on. All right, so if we're looking at this here, okay, this is obviously a nice solution. Everything is dissolved. I don't see any solids anywhere in that little test tube, right? But in this test tube, is the substance dissolved? It is not. Okay, I can clearly see that there are two parts to that mixture. All right, and so we're going to learn kind of the names here of the two different kinds of mixtures. All right, something we do need to know though is this word right here. Okay, a precipitate is a solid that forms because something is not soluble. It may be that you've simply saturated the solution and you can't get any more of the solute to dissolve. Then the rest that you add will precipitate to the bottom. Okay? And just like the word would imply, kind of means it falls out of the solution and winds up on the bottom like precipitation falls from the sky. You can also get precipitates as the result of a chemical reaction. Right, something we're gonna do in our reactions lab next week probably, okay, is that we're gonna have a couple of reactions that will actually form precipitates. So we'll have two clear solutions, and when we put them together, we're gonna get like a powder just falling out, okay, of that solution. One of them is like quite immediate and bright and obvious, okay. So what happens is basically you take two materials that are both soluble in water, and then when you mix them together, the chemical reaction occurs and produces two new materials, one of which isn't soluble in water, so it falls out. It precipitates out of the solution. It's why a precipitate is one of the signs of a chemical change. Okay? It means that you have definitely made something new, and it has different physical properties than the stuff you started with. Okay? So the word precipitate means a solid, okay, that forms and then kind of, it doesn't always have to fall out of the solution, it could also float on the top depending on its density. All right, so terminology. If I get a mixture that contains a solute, that's the thing getting dissolved, okay, completely dissolved in a solvent, okay, then I have a true solution, or what we call a homogeneous mixture. Okay, so a solution is a homogeneous mixture. Right? And the reason we call it that, homogeneous, is because the prefix homo means one, okay, or alike, okay, or something along those lines. Okay, so if I have a homogeneous mixture, it means it's all one part, okay, or it's all the same. Okay, does everyone kind of follow me there? And then if I have a mixture but I can see two or more visible parts, then I don't have a solution. Okay, and the reason for that is because the thing is obviously not dissolving. If I stir it, I might be able to suspend it, okay, in the solvent, but I can't actually get it to physically dissolve. That means I have a heterogeneous mixture. Okay? Hetero meaning many, okay, or more than one. Right. Sometimes we also call it a mechanical mixture. Okay. We don't usually refer to, liquid, aqueous kind of things as mechanical mixtures, but they can be. A mechanical mixture would be like iron filings in sand, or if you go to like a sandwich shop and they have one shaker that has both salt and pepper in it. Okay, Subway does that, I don't know why. Okay, but they have the salt and pepper in the same shaker. That's a mechanical mixture. The pepper's not dissolving in the salt, and neither is the salt dissolving in the pepper. Okay, they're mixed around, okay, but they're not one visible part. Okay, so mixture on the left. Homogeneous or heterogeneous? Homogeneous, one visible part. This, heterogeneous or mechanical mixture. Okay, obviously two visible parts there. Okay. All right, does that sound familiar? Okay, and then other definitions here. Solute. Okay, the definition of a solute is that it is the substance that is being dissolved. Okay. So if I'm putting, for some reason I decided to pollute my coffee with sugar, okay, which I don't. It would be, okay, that would be, the sugar would be the solute. Okay, it would be the thing that's going to dissolve, right? If you're making hot chocolate or lemonade, you put the powder in, okay, it's going to dissolve. Right? And then the solvent is the substance that will dissolve another substance. In most cases, for what we're doing, the solvent will be water, right? It doesn't always have to be water, okay, but it usually will be. And which is also why we refer to a lot of cleaners as solvents, like Mr. Clean or Pine Sol or whatever your preference is, CLR, okay? Those are all solvents. They help to dissolve things that don't dissolve in water very quickly, like hard water scales and soap scum and things like that that might be, on the inside of a shower or a coffee maker, okay, or something like that. Water's not going to dissolve those very quickly right? So we put in a solvent, okay, they're more soluble in. Right? Similarly, if you were to, let's say, stain your deck or your fence or something, okay, with oil-based stain, can you get that off with soap and water? Okay, they're not, so those things are not soluble in water. What do you have to use instead?
Solvent,
Yeah,
cleaning product.
cleaning product like paint thinner, okay, Varsol. I wouldn't recommend these, but they work, diesel fuel and gasoline, okay? They will also, they have that whole like highly flammable thing, not that Varsol isn't flammable too, but, okay, all those things will dissolve oil-based materials, okay, and so thus they will take them off, okay? But you have very great difficulty taking them off with soap and water. All right. Questions on those? Definitions are familiar? Okay, and then we got precipitates, okay, which is any solid produced in a reaction that will not dissolve in solution. Now I'm going to show you this movie, which is just a YouTube video. It's not like life-changing or anything, but I'm going to warn you ahead of time. It has the most oddly chosen soundtrack. It has this melancholic Italian guitar music playing in the background. It always makes me sad when I watch it just because of how it sounds. But the video is a good video showing a precipitate forming. Okay, so just gotta pause my recording or YouTube gets angry. All right, so that's precipitate that we saw. There's not a big precipitate. Like we're gonna do one where the mixture will become chunky. Okay, like as soon as you mix the two together, it just gets chunky. Right? Some precipitates are like that, okay? Some precipitates are very fine, like that stuff was, okay? And other precipitates are like thick, they can even become like gel-like, okay? All depending on what their structure is. Okay, so precipitate, as we said, was any solid produced in a reaction, will not dissolve in the solution, okay? And then solubility, the definition of solubility is the degree to which a substance will dissolve in another substance. Okay, it's a characteristic physical property. Okay? Some things have high solubility, some things have lower solubility, and we generally measure that in moles per liter. Okay, that is how many moles, which is a unit of chemical measurement we'll talk about later, can actually be dissolved in 1 liter of water. All right, picture there. Twinkies, the modern Twinkie, is soluble in water. Does that seem odd? It is kind of disgusting, in as much as it's supposed to be pastry. Okay? The original Twinkie had lots of natural ingredients in it. You know, like the things you should find in cake. Eggs, milk, okay, flour, sugar, okay, things like that. In fact, the original Twinkie even had banana filling. Okay? Not the white, so close to plastic, it's almost plastic filling, right? So the original Twinkie, made by Hostess, okay, was cake. If you put it in water, it would act like a sponge, like cake should. Not that you should put cake in water, but okay, it would just suck up the water, soak it up. It wasn't soluble because it had oils. Okay? It had, the stuff from the eggs, the stuff from the cream, from the milk, the butter, okay, that was used to make it. All of these things, they weren't soluble in water. It just made it able to absorb water. Well, the problem with the original Twinkie was it was made of natural ingredients. And what happens to natural ingredients if they're on the shelf for a few days?
Expired.
Yeah, exactly. So Hostess didn't like that if they sent a Twinkie to a store to be sold, it only lasted on the shelf for a few days. Okay? A lot of them ended up getting thrown out. You don't make a lot of profit that way. Right? So they started looking for ways to replace some of the natural ingredients. In fact, to an extent, history forced them to do that because there were shortages of some of those ingredients during World War II. Okay? So they started changing some of those ingredients. They substituted like albumin powder for eggs. Okay? If you've ever had powdered eggs, that's what you're eating. Okay? It's like dehydrated, semi-real eggs. Okay? Powdered milk. Okay? High fructose corn syrup instead of regular sugar. Okay? Oils, kind of like unsaturated fats were replacing the butter, okay, which is a saturated fat. Right? Lots of artificial ingredients went in there. And then they said, okay, so we have less natural ingredients. But now look at the Twinkie. As soon as you take eggs out of the equation, what very characteristic property of the Twinkie will also be lost?
The sponge-like nature.
Not even the sponge-like nature. What color is it? The Twinkie is yellow. It gets that yellow color from egg yolks. But as soon as you replace the yolks with something else, a Twinkie looks like it's made out of drywall. It's not nearly as appetizing to look at a gray Twinkie. Okay? So, they had to put in something to get the color back to where it was supposed to be. Yellow dye number 5. Yellow dye number 5 is banned by the Food and Drug Administrations of most countries. Canada and the US being notable exceptions. Okay? It is a known carcinogen. That means it causes cancer. Okay? It's not good for you. Now, the Food and Drug Administrations of our country say, yeah, but in small amounts. Like, as long as you don't live on Twinkies, which you shouldn't do, and you won't live long if you're trying to live on Twinkies. Okay? It shouldn't be a problem, right? Everything in moderation, it's not that big a deal. Okay? So we got that replaced. But Twinkies then, their shelf life had gone up to a few weeks. Right? And that still was like, that's not great. Still a lot of these are getting thrown out. If we could make the Twinkie last for months, or maybe even years, then we wouldn't have to worry about losing so many. So we're going to put things called preservatives in them. Okay? Now preservatives are obviously things that prevent the growth of bacteria and mold and things like that. Which means they have to be, to an extent, toxic. Okay? So that the Twinkie doesn't seem appetizing to fungi and bacteria and things like that. So they won't grow on it. But that also means that you're ingesting said toxic chemicals that prevent the growth of bacteria and mold and things like that. Okay? So they put these preservatives in there. And this is why, and I'm not one of those people that I only eat organic food, because I eat crap. Okay? I totally eat all of these things. So I'm not like giving you a nutrition lecture like you have to switch to organic right away. Okay? But I'm saying that, yeah, there's a lot of that stuff that's in there. And a lot of it is soluble in water. Hence, when you put a Twinkie in water, very soon you will have that. That's not barf. Although it makes, when you think about what's in one, it makes you want to. But okay, it's a dissolved Twinkie. Even the filling, which used to have butter in it, which we know does not dissolve in water, is like completely dissolved. Okay? So lots of things are soluble that maybe shouldn't be.
Do you still eat Twinkies?
I don't eat Twinkies, no. I don't know that I ever ate Twinkies, actually. Cake in a tube form just seems weird. All right, now you imagine some of the other things we eat, that last forever if you don't open the packages, okay, like hot dogs. I mean, you know what hot dogs are made out of, right? Okay, so there's lots of preservatives. Obviously, some of them are not natural preservatives. Is salt a preservative? Yeah. Okay, I mean, we knew that if we dried food and salted it, cured it is what the process is called. That's how you make beef jerky. Okay, or any kind of jerky. It's also how like salted meats like salami and pepperoni and things like that are made. There's curing salt in there. Okay, so they last a long time because the salt keeps stuff from growing on it. Not as well as mortician's fluid. Okay, which is the same preservative used in Twinkies. You guys know what mortician's fluid is for?
Dead body.
Yeah, it's what they use at a funeral home to keep the body from smelling. Yeah. Okay, so it's gonna prevent the growth of bacteria and stuff well. Okay, but I don't intend to have any of that in me until I'm required to have it in me. Yeah. Okay, making sense? Okay, so the definition of solubility is how much of something will dissolve in something else under certain conditions. Okay. All right, solubility chart. Okay, so let's have a look at how this is going to work. Okay, don't worry about these ones on the side just yet. So if everyone can just take out that solubility chart, it's on the back of your periodic table. So the solubility chart works like this. It'll tell us whether something is soluble or It's only slightly soluble. They say slightly soluble, we're gonna say for all intents and purposes, insoluble. In other words, it would form a precipitate, okay? So what we do is we look at the first row of our periodic table here, okay? And you'll notice that in that first row are basically all of the negatively charged parts of an ionic compound. All right, so in this first one here, it says group 1 ions, and then these 5 other things. That would be ammonium, nitrate, chlorate, chlorite, and acetate. Okay, so, sorry, which one's group 1? Group 1 is right here. Okay, it's the first group. Okay, so the group numbers are at the top of your periodic table. Okay, so everything in group 1. Okay, so solubility, okay, and so then the next row down says these are the things that are very soluble with this. Okay, so if I've got ammonium, it's going to be soluble with pretty much anything. Okay, if I have nitrate, it's going to be pretty much soluble with anything. Okay, so that basically means that anything in that first row, lithium, let's say nitrate, or like lithium, sodium chloride, or whatever, those are all going to be soluble. Okay, because they contain group 1 ions with something else. Okay, so it says most. Now, most is not a great way to fill in a chart. Okay, it says most. If you are looking at something and you're not seeing it, or you're seeing most, look down in the row below. Okay, you're going to have to check the row below. Okay, so basically this most means everything is soluble with this except for these 4 things. Okay. So when we're looking at these rows here, okay, don't just look at most and go, oh, that means it is soluble. Double check down below. Okay, so let's say I have this compound here. Let's say I've got lithium hydroxide. Okay, and I want to figure out whether that's soluble or not. So what I do is I find the non-metal part, or the negatively charged part up here. Okay, and I can see that OH hydroxide is way over here on the far end of the table. Okay, the table says it is soluble with group 1 ions and ammonium, and not soluble with basically everything else. Okay, because we see most is down here in the slightly or not soluble row. Okay, so does that mean lithium hydroxide is soluble? It does, because where is lithium?
Group 1.
It's in group 1. Okay, does that sort of make sense how that works? Okay, let's try a slightly different one here. Let's try lead 2 iodide. Okay, so if I want to figure out if this is soluble, I find the negatively charged part of it. That would be iodine. So I go to the top row. Here's iodine right here. It says it's soluble with most things. Yay, helpful. Okay, so now I got to look down in the row below. It's not soluble with copper, silver, mercury 2, and lead 2. Okay, is that stuff soluble or not? No. Not soluble. Is that a pretty easy chart to use? Okay, try these 8. Write them down, and using your chart, write S or NS next to them. Soluble or not soluble. Okay, we'll go through those in a couple minutes. All right, so our first one is calcium sulfate. All right, so I got to look for the negatively charged part of that, which is sulfate. Okay, and it says that sulfate is soluble with most things, but it is not soluble with, well, with calcium. So this stuff is not soluble. All right, potassium hydroxide. All right, so I find hydroxide, it's right here. It says it's soluble with group 1 ions. Is potassium in group 1? So that stuff is soluble. Okay, lead 2 chloride. Well, we've already done lead 2 iodide, and chlorine is in the same row or same column. So chlorine is soluble with most things, but I see lead down here. Okay, so that stuff would be not soluble. Okay, tin 4 fluoride. So fluorine has its own column. Okay, fluorine is right here. It says it's soluble with most things, but not with lithium, magnesium, calcium, strontium, barium, iron, mercury 2, or lead 2. So I guess tin is part of most. So this stuff is soluble. Yeah. All right, then we got copper 2 sulfate. So sulfate is right here, okay, soluble with most things. And I do not see copper listed down here with the not soluble stuff. So this stuff would be soluble. Okay, and then we have potassium bromide. All right, so we find bromine is right here. Says it's soluble with most things. And I do not see potassium listed here in the not soluble row. So that one is soluble. Okay, silver fluoride, so fluorine is right here, soluble with most things. I don't see silver listed down here in the not soluble, so that one is soluble. And then we have beryllium nitrate. Well, nitrate is soluble with pretty much everything except these extravagantly odd and rare polyatomic messes. Okay, so that stuff is soluble. Okay, so here's how this is going to most commonly play out for you. When we get into reactions and we start predicting the products of reactions, which, fear not, is still like a week away, okay, you're going to be asked sometimes to tell me whether any or all of the products are soluble. Okay, so if I had a reaction, let's say like this, okay, so magnesium chloride is going to react with sodium hydroxide. When that happens, okay, and it's not necessary for you to know this yet, but it's going to make magnesium hydroxide and sodium chloride. Okay, then I would ask you, all right, which, if any, of the products are soluble? Right? Now, this one's kind of a no-brainer because we all know that salt is soluble. I mean, we could double check it on the chart, it's not a bad idea, but salt dissolves in water. Okay? Magnesium hydroxide may or may not. Okay, so I find hydroxide soluble with group 1, soluble with ammonium, not soluble with everything else, which would include magnesium. So that would be not soluble, which means that reaction would produce a precipitate. Okay, that sort of makes sense? That's what I would ask. We're not there yet, but this is the solubility part. So. Okay, questions on the solubility part? Okay, well, let's talk about water then. Okay, so when we're talking about molecular compounds, we said that molecular compounds share their electrons. Okay, and so those bonds are very, very strong because they have to have each other in order for those outer shells to be full, right? And then everybody is happy. Okay? It's not like the ionic compounds where the electrons are just given away. Okay? So in a molecular compound, electrons are shared, but it's not as nice as it sounds. Okay? Some nonmetals are better at sharing electrons than others. Oxygen is not good at sharing electrons. It is what we call highly electronegative. On your periodic table, in each element's box is a number below the atomic number. Okay? So in, let's say, hydrogen's box, okay, below its atomic number of 1, is its electronegativity, 2.2. Okay? This number tells us how strongly something holds on to its electrons. Okay? So hydrogen's number is 2.2. Oxygen's number is 3.4. Okay? And there's really only a couple of things on the periodic table that are more electronegative than oxygen. Fluorine being the best. Okay? 4. I don't think there's anything bigger than that anyway. Okay? So really, fluorine and oxygen really hold on to their electrons very, very tightly. Which means then that the electrons spend more time around the oxygen than they do around the hydrogen. Okay, so what's really going on here is that hydrogen's got this single electron that it's supposedly sharing with oxygen. Okay, that electron is supposed to orbit or go around or spend time in orbitals that are around the hydrogen atom. But because hydrogen can't hold on to it nearly as well as oxygen, that orbit becomes more like, instead of being circular like this, becomes more like this. It kind of becomes elliptical. And it spends more time closer to oxygen than it does to hydrogen, which actually gets worse and worse. That electron actually doesn't even go past hydrogen. It just does this. Okay? That orbit, we'll call it weakly an orbit, ends up being more like this. Okay? Which leaves a proton sticking out the top of a water molecule. And what charge do protons have? They're positive. Okay? So this electron that's supposed to be going around and around here isn't there. So there's this highly charged proton, positive particle, sticking up here, and another one sticking up over here. And then there's all these extra electrons hanging out down here. So the molecule becomes polar. That is, it has positive ends and negative ends, instead of being all balanced and sharing everything nicely like is implied in a molecular bond. Okay? This is what we call a polar covalent bond. Okay? A molecular bond is also called a covalent bond. Right? Some of those covalent bonds are mutual and equal and happy and nice. Okay? But polar covalent bonds are not. Okay? The oxygen is like that friend you don't invite over when you're having pizza. Okay? They're the friend that in a pizza that has 8 pieces eats 6. Okay? Now maybe you're okay with that. Maybe you're watching your calories and you only want 2 pieces out of the 8. Okay? But this is not the case. Okay? This is oxygen eating 6 of 8 pieces and leaving 1 piece for each of the hydrogens. Okay? Not sharing well. Right? And so the electrons end up down here, and so we end up with 2 positive charges at the top of a water molecule and kind of 2 negative charges at the bottom. Every water molecule is going to look like that. So when another water molecule comes by, what could happen? If you've got a positive end and a negative end, and another water molecule that also has positive and negative ends comes by.
They'll stick together.
Yeah.
Or repel each other.
Yeah, they'll attract each other. Okay? If the negative end of another water molecule happens to come by here, so okay, so here's another water molecule. Okay? If the negative end of that water molecule comes by here, it's going to be attracted to this positive part. Okay? And they'll form what's called a hydrogen bond, because hydrogen's involved. Okay? So they'll form this hydrogen bond and they'll link up. Now hydrogen bonds aren't strong. There's nothing really in it for either one of them. They're just, oh, you're positive and I'm negative, I like you. Okay? And so they come together. Right? Hydrogen bonds can break very easily as well, but they also reform very easily. You've probably seen this behavior with water. It's what causes surface tension. Okay, so if you've ever seen a bead of water on the hood of a car or on the leaf of a plant, okay, or even on a window sometimes, okay, you see that water just forms these beads. And sometimes those beads will stick to the side of something. Like if you've got a really cold drink in a glass, you'll see water starting to bead on the outside of the glass, but it'll hold on there. It won't slide down the glass until it gets too big. Okay, that's all caused by water being a polar molecule. Okay? These little hydrogen bonds are strong enough to hold that bead of water against the side of the glass. Okay? If you were to do that with something that wasn't polar, like if you took an eyedropper and put a drop of alcohol, okay, on the side of the glass, it would immediately run down the side. Okay? Because it's not polar. It doesn't have that surface tension. It can't do that. Okay? You probably notice you can also fill a glass slightly more than full because of that surface tension. But as soon as you touch it, it's gone. Okay? The hydrogen bonds are strong enough to hold that until it's disrupted. Okay? It's why you can skip a rock across the water. Okay? It's why some bugs can float on the surface. Okay? They don't break that surface tension. They're small enough, they spread themselves out enough that they don't break the surface tension of the hydrogen bonds of this polar molecule. Okay, everybody with me so far? Okay, so like we said, the sharing isn't equal, okay, because oxygen is more electronegative, okay, than hydrogen is, so it holds on to those electrons more, and you end up getting this. Okay? Water molecules can form hydrogen bonds with other polar molecules, most often with other water molecules. Okay? And so we get these hydrogen bonds, and that's what creates surface tension. Okay? Now, what's another thing that water does that most other things do not do? It expands when it freezes. Until about 4 degrees Celsius, water behaves like everything else. Okay, it contracts. So if I have water at 85 degrees and I have water at 4 degrees, they're going to have a slightly different volume. Okay, because just as anything else, when it starts to get cooler, it's going to contract. Now, most things, when they get to close to their freezing point, they continue to contract. They'll turn back into a solid, and the solid will continue to contract. Okay, water is not like that. When water gets to 4 degrees Celsius, okay, the water molecules start to get too close to each other. And remember, they have charged ends. So when you start pushing them close to each other, you start pushing the positive ends close to other positive ends, and negative ends closer to negative ends, and what do? They repel. So there's this, almost like you're compressing a spring, and you just can't hold it anymore. You've got it so tight, and then all of a sudden it just back out. Okay, that's what water does, just as it freezes. Okay, you force those molecules together to the point where they just can't take it anymore, and they pop back out. Okay, and that's why if you freeze a bottle of water, okay, like a plastic bottle, the bottom of it like pops out. Okay, because ice takes up more space than liquid water. Which actually is a really important behavior of water, because it means that ice is less dense than liquid water, which is important for the survival of all aquatic organisms in areas where lakes might freeze or rivers might freeze. Okay? If ice was more dense than water, lakes and rivers would freeze, right? Or actually from the bottom up. Okay? Because ice is less dense, the top freezes first and insulates the bottom against the cold outside.
It's also important that it's insulated.
Yeah, yeah. Well, I mean, snow is a way better insulator than ice, but just having that block of solid material between the cold air and the water beneath, okay, is important. Okay? You can still get some lakes freezing all the way to the bottom if they're in really northerly areas or high alpine or whatever. Okay? But in general, that protects the organisms that live in that water. Okay, so a polar covalent bond is one in which the electrons are not shared equally. So when it comes right down to it, what you need to know about water is this. It's a polar molecule. Polar molecules don't share electrons equally. That means one end is positive and one end is negative. And it can form hydrogen bonds with other polar molecules. Okay? If you can explain those things to me, okay, on a test, you're good. That's what you need to know about a polar molecule. Okay? Because let's say I was to, spoiler alert, give you a question that asked you about water and its behaviors, I would want to have those things in an explanation. Okay? What is a polar molecule? Okay? How does it happen? Hydrogen bonds, what does that look like? Okay? What's maybe an application of that? How does a living organism use it? Okay? Something like that. And we've only talked about the bugs and the aquatic organisms. We haven't even talked about how this is so necessary for trees to transport water from their roots to their leaves yet. Okay? Also a big deal. Okay, so we talked about that already. And this is what we were talking about with water, okay? When you're looking at liquid water, the molecules are really close together, but when it turns into a solid, we get a crystalline shape, we get them moving further apart, okay? And is that crystalline formation, is it like predictable?
No.
It's not. Okay, you ever hear that expression, there's no two snowflakes alike? It's not true. I mean, there's lots of snowflakes that probably look exactly the same. Okay, but they can have lots of different shapes. right? And that's because of how this crystallization process occurs. They just push away and they freeze and you get that crystalline shape. Okay? And it's lighter, obviously, than its liquid counterpart. All right? Those hydrogen bonds can form between any polar molecules. So another example of a polar molecule is ammonia, or nitrogen trihydride. Okay? Also doesn't share its electrons equally and can form hydrogen bonds with water. Okay, so how does this affect living organisms? Anybody ever play with a barrel of monkeys? Maybe those plastic monkeys with the arms and legs hooked together? Okay, that's kind of how water is when it's going up the trunk of a tree or the stem of a plant. Okay? Plants don't use any energy to move water from the ground to their leaves. Even though they're lifting it against gravity, they don't use any energy to make that process happen. It's all free. Okay? What happens is water evaporates from the leaves. But because water is polar, it's hydrogen bonded to other water molecules, like barrel of monkeys are hooked to each other. Okay? So if you ever played with those, you know you could hook them all together and lift up a whole string of them by only pulling on the top one. Okay? Everybody with me there? That's how water works inside the trunk of a tree. It hydrogen bonds to other water molecules. So if one of them goes out the leaf, it pulls on all the other ones, okay, and brings them up as it goes. They can also hydrogen bond to the inside of the stem, okay, and that helps to support their weight. So you get a hydrogen bond here between two water molecules. We call that cohesion. And you get a hydrogen bond between the water molecule and the stem. We call that adhesion. Okay? Those two words are important. Okay? Cohesion, water to water. Adhesion, water to anything else. Okay? So like an adhesive is used to glue two non-like things together. Adhesion. Okay? Cohesion means to stick together with things that are like you. Okay, so without water being a polar molecule, plants wouldn't be able to transport water from their roots to their leaves. Okay? So if you were looking for, let's say, the fifth mark in that question I spoiled, okay, living organism using the polar nature of water, a plant would be a great example. Just saying.
Would you also be okay if we just talked about bugs on the surface tension of water?
Yeah, that could also be one. Okay, so you see cohesion is in here. Okay, cohesion is that bonding of two like things, or in this case, water to water, right? And then we have adhesion. Okay, that is the clinging of one substance to another, right? These are some examples of what that cohesion and adhesion look like. Cohesion is what makes the bead shape. Adhesion is what sticks it to the leaf. Okay. Everybody all right with that? Now, why do plants want to have water do that? Don't peck up there.
It was adhesion?
Yeah, why do they want the water to bead like that and not penetrate the leaf?
So the leaf doesn't get all soggy.
Okay, partly, yeah. I mean, we don't want the leaf to get soggy.
So it drips down to the roots.
Exactly. The leaves actually can't absorb water. So having water on the surface of the leaf is completely useless. But if they make it bead like that, eventually it gets big enough that it runs off the leaf and onto the ground where the roots are. The roots are the only part of the plant that can pick it up. Okay? So it's a good evolutionary kind of adaptation to make sure all the rain that falls on the plant ends up below it. Okay, so we talked about the bugs on the surface. Then there's also the Jesus lizard, okay, that can walk on the water. Okay, it has to move its legs really, really fast. If you ever watched a video of one, they look almost comical as they run across the water. Okay, but what they're essentially doing is using that surface tension. They do break the surface tension, okay, but fast enough that they can still propel themselves forward. Okay, for you or I, that won't work. I mean, there's no speed we can run at that would allow us to run across water like they do because we're simply too heavy, okay, and we would sink. The Mythbusters tried it at one point. They had like big foam blocks on their feet and they tried to run across
Yeah,
the
they'll be
water.
running at like 88 miles an hour.
Yeah, it was some ridiculous speed you couldn't possibly run at in order to work. Okay, but You can skip a car, just like a rock. Mythbusters did that, okay? Because in a movie called The Cannonball Run, they jumped a Lamborghini, okay? The Countach, like the 80s one with the gull-wing doors, okay? Across a lake. Okay, so they came like zipping at the lake at a high rate of speed, jumped, and because the engine is in the middle, it didn't nose down, skipped off the water to the other side. Okay, see you guys tomorrow. We're gonna start talking about reactions tomorrow.